The integral test. Suppose the function f of x is a continuous positive decreasing function for x greater than or equal to 1, and ak is the k term for the infinite series for k equals 1, 2, 3, and so forth. Then the infinite series ak, k from 1 to infinity, and the improper integral of the function f of x from 1 to infinity, either both converge or both diverge. In the case of convergence, the value of the integral is not equal to the value of the series. Summary, we are going to check three criteria of the integral test, such as number one, check the continuity of the function on the interval of interest, which is from the n to infinity, or we just check the domain of the function. And number two, is the function positive, and make sure the function f of x is positive on the interval of interest. So we can check the first few terms or do it by observation. Number three, is the function f decreasing. So we are going to verify whether it's decreasing or not by using the first derivative and see if it's less than zero, or we can do by observation by making the list of the few terms. Examples. Use the integral test to determine the convergence or divergence of the following series, or state the conditions of the test are not satisfied and therefore the test doesn't apply. For first example, the infinite series k to the third divided by k to the third plus 1, k from 1 to infinity. In our case, ak equals k to the third over k to the third plus 1. For k equals 1, 2, 3, or we can say k is greater than or equal to 1, or put in the interval form as from 1 to infinity. Since ak is a function of the k, now we're gonna use the function f of the x as x to the third over x to the third plus 1 for x greater than or equal to 1, and check whether this function continuous or not by checking the domain. This problem, the function as x to the third over x to the third plus 1, and the domain is from the denominator cannot be 0 or x cannot be negative 1. For x equals negative 1 is not in the interval of interest. Therefore, the function f of x is continuous on the interval 1 to infinity. And number two, we're going to check whether the function is positive or not for all terms x greater than or equal to 1. We can make a list by for x equals 1. So f at 1 equals 1 over 2. F at 2 equals 2 to the third over 2 to the third plus 1, or 8 over 9. F at 3 equals 3 to the third over 3 to the third plus 1, which is 27 over 28, and so forth. So they all are positive. So we can say that the f of x is positive for x greater than or equal to 1. And number three, we're going to verify is the function decreasing or not. As we see, it looks like the function is not decreasing, but we can verify using the first derivative. So we're going to find the f prime using the quotient rule. Low d high minus high d low over low squared. So we have the x to the third plus 1 multiplied by 3x squared minus the x to the third multiplied by 3x squared, or divided by the denominator x to the third plus 1 squared. Simplify to get positive 1 times 3x squared divided by the quantity x to the third plus 1 to the power second. As you see, the power 2, they all are positive. Therefore, the f prime is positive for all x, let's say all x. And in this condition number 3, we can say f of x is not decreasing for x greater than or equal to 1, which is the interval of interest. So number 3 doesn't apply. Therefore, for this problem, for this series, the integral test doesn't apply. This example, we have the series 11 divided by 7k plus 2, k from 2 to infinity. The ak term is 11 over 7k plus 2 for k greater than or equal to 2. So the function that we are going to use is in the form of 11 over 7x plus 2 for x greater than or equal to 2. Check the domain. The domain of this function is the set of x such that x is not negative 2 over 7. But we are looking for the interval of interest for x greater than or equal to 2. Therefore, the function f of x is continuous outside of the negative 2 over 7, which cover the x greater than or equal to 2. So we say f is continuous on the interval 2 to infinity. And number 2 is the function positive. It's very obvious that fx equals 11 over 7x plus 2, positive for x positive, including x greater than or equal to 2. And number 3, we're going to see if the function is decreasing or not by checking the derivative. So going to be 7x plus 2 multiplied by 0 minus 11 multiplied by 7 divided by 7x plus 2 to the power second. By using the quotient rule, it becomes negative 77 divided by 7x plus 2 to the power second, which is very obvious as the sign negative. So f prime is less than 0 for all x. Then we can say f of x is decreasing on the interval to infinity. Check. So we meet all three conditions of the integral test. So we're going to proceed using the improper integral to find the value. From the infinite series, which is 11 over 7k plus 2, k from 2 to infinity, transform into the improper integral, lower limit 2, upper limit infinity, the integrand 11 over 7x plus 2 with respect to x. Evaluate this improper integral by introducing the notation for the upper limit as a b and take the limit as b approaches infinity of the integrand 11 over 7x plus 2 with respect to x. Use the u-sub technique as u equals 7x plus 2. So differential u is 7 dx or 1 over 7 du equals dx. And this becomes the limit b approaches infinity of 11 over 7 natural log absolute value of 7x plus 2. Evaluate from 2 to b. 11 over 7 as the common factor. Limit b approaches infinity. Replace the upper limit b to get natural log 7b plus 2, subtracted by the natural log of 7 times 2 plus 2, which is 16. Take the limit. The natural log 16 is the real number. The natural log of 7b plus 2 as b approaches infinity as well. Therefore, this improper integral approaches infinity, which we say this improper integral diverges. By the integral test, this theory also diverges. Example 3C. This example, we have the AK as 5 over k squared plus 64. And the k starting from 1 2, 3, and so forth. The function f of x is 5 over x squared plus 64 for x greater than or equal to 1. The domain of this function is the set of all real numbers because no restriction. The denominator always positive. Therefore, the f of x is continuous on the interval 1 to infinity. Number 2, is this function positive for all x greater than or equal to 1? The answer is yes, because for positive x, the quantity of the f of x always positive. And number 3, is the function decreasing? We're gonna find the first derivative again, or we can do by observation. For this case, observation might be easier, but to be concrete, we use the derivative to verify it. So this is gonna be negative 5 times 2x divided by x squared plus 64 quantity squared, or negative 10x divided by the quantity x squared plus 64 power second. It's going to be less than 0 for x greater than or equal to 1 as a sign negative here. Confirm the negative quantity. Therefore, the f of x is decreasing on the interval 1 to infinity. So meet all the three criteria again of the integral test. And then from the summation, 5 over x, no, it's a k squared plus 64, k starting from 1 to infinity, transform into the improper integral, which is from the same number here, starting at 1, gonna be lower limit 1 to infinity of the integrand 5 over x squared plus 64 with respect to x. Same process, introduce the notation b for the upper limit. Take the limit as b approaches infinity. Integrand 5 over x squared plus 64 with respect to x. Then we get the antiderivative as 5 over 8 of the inverse tangent of x over 8 from lower limit 1 to the upper limit b. 5 over 8 as the common factor. Take the limit b approaches infinity. The inverse tangent of the upper limit b over 8 minus the inverse tangent of the 1 over b from replacing the lower limit. Inverse tangent of 1 over 8, this is the real number. The inverse tangent of b over 8 at b approaching infinity gonna be the inverse tangent of the infinity. If you recall the graph of the tangent, there are multiple vertical asymptotes, and the graph of the tangent will be similar to these figures. The vertical asymptote as the odd multiple of pi over 2. As it approaches infinity, that means the angle approaching pi over 2. So that tells us the inverse tangent b over 8 as b approaches infinity, approaching to the value pi over 2. Then we can see this as the value of the improper integral in the form of pi over 8 multiplied by pi over 2 minus the inverse tangent of 1 over 8, which all are real number. Since it is the real number, therefore this improper integral converges. And by the integral test, this series also converges.